So welcome. Let's have a look at this next section, which is on the interference of light waves. We've done some interference before when we did the stuff with sound waves. We'd have a speaker at one side and a speaker at the other side, and we'd ask ourselves, you know, do they come in phase? What's the path difference? All that kind of stuff. You remember that from earlier on in physics too? It's the same kind of game, but we're going to play it with light. Conditions for interference. The sources must be coherent. Coherent meaning they must be in phase with each other. So we're going to have two light sources. Sometimes we'll make one light source into two. Sometimes we'll have two light sources. But they must be coherent. It's easy to make speakers coherent. You just wire them up the right way. But light's not so easy because it comes as photons. So what it means in terms of photons is, if I just, I've got to go here, I'm sorry. If I go here, let's go to black, let's go to here. Oh, I messed something up there, didn't I? Let's go to slideshow. Let's go to here. Let's go to here. So coherent means basically, to get light to be coherent, I need to have kind of like overlapping patterns. So if that's where the maximum is, okay, let's try and draw it carefully. Let's say the wave looks like that inside this little package. So there's where the maximum is, there's where the maximum is. Okay? Then there's where the maximum is, 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 there's where the... These are coherent because they're like in step with each other. Yeah? In position or in time, whatever, they've got the right phase relationship to each other. If they're not coherent, what I'd have is this guy would be here. So this guy which went through a crest and was near a trough here would be going through a crest there. So that trough would correspond to that crest and they'd cancel each other out or whatever. Yeah. So coherence is when the photons of the wave within the photon is in step. Okay, like marching, yeah? You could imagine a group of soldiers here marching in step and a group of soldiers here marching in step and they're in phase with each other. That's coherence. If these guys are in step and these guys are out of step, then that's not coherence. And that's what you get from a normal light. Like the light coming from that projector is not coherent. They're different photons. All you know is what color they are and how intense they are. They don't matter what the wave is like. Whereas from a laser, they are coherent. And that was the amazing thing about lasers. You could make light that was coherent. Before we had lasers, we kind of got coherence kind of like in a bit of a sneaky way, which is what good old Young did. Okay. So light must be coherent. Monochromatic, that means, you know, single frequency. You don't want a whole bunch of frequencies. And it's got to follow the superposition principle. So if I put a crest on a crest, I get a crest that's twice as big. If I put a trough on a trough, I get a trough that's twice as deep. It adds up, you know, using sums. Thomas Young did a famous double slit experiment, and he did it a long time before we had lasers. So how did he get coherence? He kind of, I don't know if he looked out or he was very clever or not, but basically, I think he was very clever. He took a light source, non-coherent light source, the photons, non-coherent, and he put it through a single slit. And remember what we said about if the opening is less than the wavelength, then it appears as if it's a point source of light. So what happened was you got basically light going out like that, and when it arrived here and here, it was in phase, which meant it was coherent. So you got coherence. A photon, as far as this model is concerned, doesn't go through one or the other. That wave packet kind of goes through both. And what he noticed was a bit shocking. If he looked at the screen that was directly in front of the two slits, he got brightness. And he got another, we call them fringes. He got another fringe of brightness and another fringe of brightness working its way upwards and downwards. But in between there were these fringes of darkness, which are like shadows. But you know what? There's nothing between those two slits and that point in the screen. If he put his finger over, he'd get just like a bell-shaped brightness. If he put his finger over the other one, he'd get a bell-shaped brightness. It's only when two of them were illuminated that he'd get this pattern. And so he started thinking, why can it be? And it turned out, oh, it's interference. It's basically the photon from this one side and the photon from the other side of a phase relationship, and there's a path difference relationship. So we do that old game where we say, if the path difference is an even number of half wavelengths, we get constructive interference. And if it's an odd number of half wavelengths, we get destructive interference. Do you remember that from when we did sound? Yeah. First 2 or 3 chapters of this section. It makes sense, doesn't it? If it's a even number of half wavelengths, then you're going to get a crest with a crest and a trough with a trough. But if it's an odd number of half wavelengths, then you're going to get a crest with a trough and a trough with a crest, so it's not going to work. So he said, 2 slits act as a pair of coherent light sources. We get a pattern of dark and light fringes, that's the terminology, that depend upon the differences of the points, the difference of the point's distance from each of the 2 slits. So it's path difference, basically. We identify the fringes by its order, and we assign the value of m. Now, I do this kind of slightly differently from how the book does it. In the book kind of talks about m as being 0 and 1 and 2, and then it has 2 equations, one for the bright fringe and one for the dark fringe, and the one for the bright fringe has a half added into it. And I'd sooner just do it where this is the 0th, and then that's a half, and that's 1, and that's 3 over 2, and that's 4 over 2, and that's 5 over 2. You go on like that. And it doesn't matter if you're going upwards or downwards, it's still 1 over 2, and 2 over 2, and 3 over 2, and 4 over 2, and 5 over 2. Boom. And we call these, this language is like important, unfortunately. The 0th order fringe is bright. The 0th order dark fringe is the half. The 0th order dark fringe is the half. The 1st order bright fringe is the 1. The 1st order dark fringe is the 1.5. The 2nd order bright fringe is the 2, and the 2nd order dark fringe is the 2.5. Terminology. So in Young's double slit fringe pattern, what is the M value for the 3rd order dark fringe? Well, what's it going to be? 3, but it's a dark fringe. 3 plus a half. That's going to be 6 over 2 plus... Yeah, I'm right. 6 over 2 plus 1/2 is 7 over 2, yeah? Let's go back to our diagram. So the second order dark fringe was 5 over 2. So the third order dark fringe is going to be 7 over 2. Yeah. So there's a little bit of familiarization with that. It's not obvious. And then in Young's double slit fringe pattern, what is the M value for the second order bright fringe? Can you do that? Second order bright fringe. You had the 0th order. So second order bright fringe. What do you think it's going to be? Bright. So it's going to be a whole number. It's going to be 2, isn't it? Which is 4 over 2. Yeah? Cool. So get familiar with that. Because I'm going to ask you a question. I'm going to use that language. You know. Do you want to know something weird? Okay, let's talk about concepts first of all. If there's no path difference, then we get constructive interference. If there's an odd number of half wavelengths, we get destructive. If there's an even number of half wavelengths, we get constructive. Boom, boom, boom. My path difference. Now, I'm cheating. I'm saying the screen is so far away that these two rays are basically parallel. So here's my 2 slits, and they're going off towards this screen to form either a bright fringe or a dark fringe at that point. Let's do some math on it. And basically what we have is that these two guys are parallel, so my path difference is equal to R2 minus R1. And if I look at this triangle, I get that if there's my distance between the slits from the center of one to the center of the other, this is the angle theta that I'm going off at. That's my angle theta, which is that angle, which is that angle. Then this path difference is equal to d sine theta. So my path difference is equal to d sine theta. So for constructive interference, and, well, d sine theta is my path difference. If it is an even number of half wavelengths, then we'll get constructive, and if it's an odd number of half wavelengths, we'll get destructive. So put the value of m in there. Maybe m is 0, or m is a half, or m is 1, or m is 3 over 2. There's the value of m coming up again. So for constructive interference, m equals 0, 1, 2, 3. For destructive interference, m equals the half, 3 over 2, 5 over 2. So here's an example. Consider this Young slit apparatus. The 2 slits are separated by 500 nanometers. So the D between there and there is 500 nanometers. The wavelength of light is 100 nanometers. Light is instant on both slits. What angle will the second order bright fringe make? So there's my angle. My second order bright fringe, m equals 2. So I say m lambda equals d sine theta, so 2 times my lambda is equal to my d, that's the separation between the slits, times the sine of the angle. So the sine of the angle is equal to 200 over 500, which is 0.4. So theta is equal to sine to the minus 1 is 0.4. So theta is equal to 23.6 degrees. If I have my calculator in degrees, I get my answer in degrees. If I have my calculator in radians, I get my answer in radians. Just make sure you put down the right thing. Now, in some of the old tests, I use, so another question you can ask is, well, how far is it, how far are you away from the straight through direction for a given distance to the screen? And there's a small angle approximation. So basically tan theta becomes the same as what sine theta, I guess it is. And because the hypotenuse is about the same length as the distance for a small angle. You know that small angle approximation? My sine is opposite over my hypotenuse, and my tangent is opposite over the adjacent. But if it's a small angle, the adjacent and the hypotenuse are basically the same length. So you can fudge the math and just, But often, when I'm doing a problem, I'm not using a small angle. 23 is not a small angle. So sometimes you'd find that people would use the small angle approximation when they couldn't really use a small angle approximation. And, to be honest, I think it's kind of like one of those situations where it's true, but who needs it? Just work out the angle and then say, oh, you want to know that guy? Okay, it's going to be the tangent of that guy. And do a second step for the problem. So sometimes when you look back at the old tests, I'm using the small angle approximation, and it's kind of like, I don't anymore. I just say work out the angle, then work out your length if you need to. You know all the math you need then. You'd have to learn a new equation. Because in the book there's a new equation that takes into account the small angle approximation. And you spend a long time trying to figure out where it came from. Then you can, oh yeah, it's a small angle approximation. But you don't need it. It's one of those parts where I think sometimes we're kind of too clever. We invent something there's no need to invent because we've already got the skills we need to be able to do it. Okay, so that's kind of cool, and it happens. And I can bring if I get my act together next time, I'll bring a laser in and I'll show you it. It happens. Do you want to know something weird? Okay, good. So here's the weird thing. Let's say we turn down the intensity of our light source. So it's dim light. But I can still see the pattern. Light travels really fast. So it takes, if that screen's, say, 3 meters away, if that screen's 1 meter away, it takes the time 1 over 3 times 10 to the 8 seconds to go from the source to the screen. I can relatively easily set up a situation where, on average, I only ever have 1 photon in the machine at any one time. And so you've got to ask where you've got to kind of ask where the interference is kind of coming from, because you've only got 1 going through at any one time. Now, I suppose if it splits into 2 photons at the 2 slits, but that's photons aren't supposed to be able to do that. I'm sorry.
Is that the whole principle of the whole wave-particle duality?
It's a bit of both, yes. But it still raises, how can you justify this from a particle point of view, or how can you justify it from a wave point of view? From a wave point of view, I can say the 2 wavelets and we start all over again. But we still want to try and look at it from the particle point of view. And that raises a whole bunch of issues about what's going on. And so if you start heading towards, so how many people have heard of In Search of Schrodinger's Cat?
Yeah, the cat in the box with the ball.
Yeah. And then how many have heard of In Search of Schrodinger's Kitten? Okay, there's 2 books. The first book is In Search of Schrodinger's Cat, which is the older version, and they're introductions to quantum mechanics. So if you have any interest in this, and you want a relatively light introduction to them, the 2 very good books, In Search of Schrodinger's Cat and In Search of Schrodinger's Kittens, and it brings out some of these problems with some of the quantum stuff, that seemingly impossible situations, and tries to resolve them, or at least give you a resolution for them, even though sometimes the resolution seems really far-fetched. So just it's the beginnings of the weird stuff that comes into physics, and modern physics for sure, as we go on. Okay. Let's draw our line there. Okay. Cool. I'll see you guys